This video is going to cover common measures of disease frequency. So disease is typically measured as binary, so diseased or not diseased, although there's a lot of illnesses that the actual measurement that you take to diagnose it will be continuous. An example is blood pressure that will have a range of values from low to high, representing a normal distribution, but we typically dichotomize it into high blood pressure and low blood pressure, even though it originally came from a continuous measure. So from here on out, I'm going to talk about disease as something categorical that it is or it isn't. There's a lot more things to count than just disease. You can count deaths, births, degrees, all kinds of things. And they don't need to be bad things either. Like degrees. The three main things I'm going to talk about are counts, proportions, and rates, as well as something called odds that's going to come up at the end, or at some point. So counts is just the number of times something happens, like 10 cases, and it represents the numerator in pretty much all of the other measures of frequency. So a proportion is the number of times something happens over the number of opportunities it had to occur. So if there's a population of 100 people, that's 100 opportunities for a case to occur, and 10 occurred. So the proportion would be 10 out of 100. It's just your classic kind of percentage if you were to multiply it by 100. It doesn't have units though, and it is sometimes called a risk. You might see it used incorrectly in the literature, things that are referred to as rates that are in fact risks. The only time something's a rate is when there's time in the denominator. So a rate is the number of times something happens, a count, over the time that was available for it to happen. So the amount of time we were looking for it, basically. So if we observe 10 cases over 2 years, that would be 5 cases per year. And this requires two measures, basically one to measure who's disease negative and another to measure who became disease positive over some time span. So yeah, these are just kind of not specific to epidemiology. Now we're going to get into some of the measures of frequency that are common in epi. So prevalence, that's the amount of disease in the population right now. And this is going to be a very disease-centric video, but you can measure the prevalence of exposure too, or really anything. But in this case, we're mostly interested in disease, so prevalence is the amount of it in the population right now. And this includes everyone who already has it, who got it at some time in the past. So it's the number diseased over the population size. So in this example, we have 20 people who got the disease and 80 people who didn't. And it's a population of 100 in total. So it's the 20 who got the disease over the population size, so prevalence of 0.2 or 20%. For visualizing a population, if some people are visual learners, this might help. Then we have this group of people, I forget how many there are, but 1, 2, 3, 4, 5 are disease positive. I guess there's 26, I'm just going to trust that there is. So the prevalence would be 5 over 26, and note that that denominator includes the 5 that were diseased. So we have 5 that are diseased out of everyone, including those 5. And yeah, that's not about 19%. Period prevalence is something you might see. It doesn't make a ton of conceptual sense, but it comes up a lot. It comes up in like most lectures like I'm doing right now that are talking about disease frequency. It's the number of cases over some time window, and that's both those that, this is how it's different from incidence. It's both those that are existing and those that occur during that window over the average population size during that window. So like, you take the initial size and the final size, and that would be how you would find the period prevalence, but I've never seen it used in any serious setting. Odds is something that I am going to contrast with prevalence here. So this is our same population that had 20 disease positive individuals out of 100. And this is also a probability. Prevalence is a probability. 20 over 100, 0.2. Odds, on the other hand, is the probability of disease over 1 minus that probability. So our probability of disease, same as before, it's essentially the same as asking for prevalence of disease. So 20 over 100 over 1 minus that probability of disease. And that comes out to 0.25. But whenever you're talking about odds, you're never going to go through that. Like it's not that much in general, but you can make it even shorter. Generally with odds, we just do number diseased over number not diseased. And that's because technically that's what this boils down to, and that's a lot faster than calculating the prevalence and 1 minus the prevalence. And I'm going to show you why it's just 20 over 80 will get you the same answer. Odds of disease, saying probability of disease over 1 minus probability of disease is the same as saying probability of disease over probability of non-diseased. So 20 over 100 divided by 80 over 100, and that also comes out to 0.25. But we can break down what's happening here even further. That's 20 divided by 100 divided by 80 divided by 100, and to put this together you just multiply it by the reciprocal, so switch that and multiply across, and then you can cancel out these hundreds and you just have 20 over 80. So we could have saved a step. If we knew that odds was our goal, we could have just done 20 over 80 and been done, rather than making it more work than it needed to be. So with an odds of disease of 0.25, that can be interpreted in kind of a more understandable way is for every one diseased person, there's 4 non-diseased people. The next measure of disease frequency I'm going to talk about is incidence. And incidence is the amount of newly occurring disease over a period of time. And incident cases are those who went from being disease negative to disease positive. So that requires 2 measures. It requires one to establish who is disease negative, because if we're just taking one measure and figuring out how many people have disease, we're finding a prevalence. But for incidence, you need to first get this group of non-diseased people, wait, measure again, and figure out how many people became diseased over time. There's 2 kinds. One involves time and one does not. So cumulative incidence and incidence density are the 2 types of incidence. Cumulative incidence, they have the same numerator. They're both the number of events over follow-up. But with cumulative incidence, it's just the number at risk at the start. And with incidence density, it's something called person time at risk that I'm going to talk about more in a second, but it's basically the amount of time that each person contributed to observation. So there's no time in the denominator of the cumulative incidence one, while there's time in the incidence density denominator. Cumulative incidence is a proportion, and in that way it goes from 0 to 1, while incidence density is a true rate that can exceed 1. Follow-up needs to be complete and the same for everyone in the population for cumulative incidence. Incidence density, since we're figuring out what everyone individually contributed, then the time that everyone is followed can vary from person to person here. Cumulative incidence is much better for a closed population, and I'm going to talk a bit more about what a closed population is. Basically, it's when the number of people in the study stays the same over time. There's no people dropping out or being added. And an open or dynamic population is one where people are free to leave and be added throughout. And again, that's permitted because we're making no assumptions about everyone being followed for the same amount of time. We're tracking down how much time each individual contributed, so we need no assumptions, and that allows for people to come and go. And again, cumulative incidence, you don't generally have data on individual people for how long they've been followed, but with incidence density, you need to have that. So just to illustrate cumulative incidence, again, it's the number of events over the follow-up period over the number at risk at the start. And this is a closed population. Everyone was followed the whole time, and there were no losses, and no one was added halfway through or anything like that. These blunted ends are those that didn't have the disease, and the circle at the end is those who had the event, and they were followed for 4 years. So there are 4 people at risk That's our denominator at the start. 2 had the event at some point over the 4 years, and 2 didn't. So our cumulative incidence is 2 over 4, or 0.5, and that has no units because it's a proportion. And I had these 2 at the end, but really they could have happened at any time, because typically a lot of diseases you can only get them once, like chickenpox, something like that. And yeah, you can just assume that once they have the disease, they're no longer at risk. These are rough approximations of what I just described, where something I said about cumulative incidence is there can't be withdrawals, there can't be people dropping out. But if there are some, and you know about that, and you still want to calculate cumulative incidence, there's some kind of crude ways you can do that. And basically, an example of how that would go down is the number of events over the initial population minus half of the withdrawals. And what's going on with this half here is that we're kind of making the assumption that those who withdraw are withdrawing at like regular intervals throughout that averages to having withdrawn halfway through, where like some people might have withdrawn right at the beginning, some right at the end. So on average, they withdrew halfway through. Another one is number of events over average population size. The average population size is the number at the beginning, the number at the end divided by 2. And neither of those are very useful, but again, it's things that usually come up when people give a lecture like this. So now we're getting into censoring, and this is just kind of introducing to incidence density. We're switching gears now. So with right censoring, it's when people are being followed, but not the entire time. So their time being followed was cut short before the end of the study. This does not count as censoring. This person's observation stopped because they had the disease. This arrow person, and that's to represent that, like, I guess the shorthand, the thinking there is that the disease happened somewhere to the right that we don't know about. That's what the arrow is about. But basically, a lot of things could have happened here. They could have stopped showing up because they moved away. They could have died of some other disease than the disease of interest. They could have withdrawn because they didn't want to participate. And this person who is followed all the way through and didn't get the disease is technically censored, but they were censored just by virtue of the study ending. Left censoring is when people join the study after it starts, and we don't have complete information on them. We don't know what happened to them here. So pretty much that's the definition of censoring, is information is missing either to the right or to the left. And most open populations, this is an open population, there are additions throughout calendar time, and there are people dropping out before the study ends. And that's what an open population is. It's much more realistic for studies in the real world, where people are typically dropping out over time, and to maintain sufficient power, studies are often recruiting people over time. So calculating incidence density, it's the number of events over person years of observation. So just to illustrate person years, it's basically counting the time contributed from each individual. So this person contributed 1 year, this person contributed 2 years, and so did these other 2. Everyone here contributed 2 years, and that's a total of 7 person years. So there were 2 events over 7 person years, so 0.29 events per person year, and that's units rather than a proportion that has no units. As far as approximating incidence density, again, incidence density is number of events over person time. There's some approximations, so you could do number of events, and that's basically, there's time here, that's the same, but this person's part is being approximated by the number at the start minus the number that are sick minus the withdrawals plus the additions, and this half each time is basically like in that other formula I was talking about earlier, where it's assuming that the number people are getting sick kind of periodically throughout. And again, the reason we're subtracting the sick is because they're no longer at risk once they become sick. We're not going to contribute them to person time anymore. And we're saying that each of these things is happening about, on average, halfway through the study. Another one is just the number of disease negative at the start minus the number of disease negative at the end times 2. That's like the average number in the study times time. And these are very crude approximations that are worth talking about, but at the same time, like I don't think they would be justified in most real scenarios. I guess two other things I decided I wanted to talk about, I guess, were morbidity and mortality. So morbidity is having the disease. So a town that has a high morbidity of obesity means there's more obesity there than usual. An individual with comorbidities means they have more than one disease at a time. Mortality is death from a disease. So the mortality for this disease is high, means that those who get it typically die from it. So these are some other frequency measures. Case fatality rate. So a disease that's particularly deadly, the number that die from the disease will be a high proportion of those who have it. So it's like saying the prevalence of death among people who have this disease. The proportional morbidity is, you can also do it for mortality. It's the number of cases of disease X, so the number of cases of cancer over the number of cases of all disease. So it's basically like a public health measure trying to figure out where this disease stands in relation to all of the disease. So like it's more useful for mortality and tracking over time and stratifying by age. So like you might see that like in people under 30, all of a sudden suicide is contributing way more mortality than like anything else, because it's hard to young people don't die of a lot of things, and they also commit suicide. So that would be a time when that's really useful to put it in the context of all diseases or all mortality. Attack rate is kind of cool. Attack rate is the number of exposed cases over the number exposed, and why it's kind of cool is because it was one of the first statistics I learned taking an epidemiology course in undergrad, where the prof had like a really neat exercise where there was like it was talking about like a picnic where some people got food poisoning, and we were trying to figure out what dish was causing it. So like we had like hot dogs and hamburgers and stuff, and if we're trying to find the attack rate for hamburgers, we'd find the number of people who got sick who ate hamburgers over the number who ate hamburgers. If we were gonna do hot dogs, you do the number of cases who ate hot dogs over the number of people who ate hot dogs, and we pretty much find whatever food had the highest attack rate, and we can be pretty confident that's the one that people got food poisoning from.